No. Well, just check. I think we're on the hour, so we'll give a nice prompt start. So good morning. Thank you very much for coming in, especially on a day which is so lovely outside and also straddling into Canada Day. Of course, we are speaking today on the traditional and unceded territory of the Musqueam people. Always interesting to think about how this intersects with things that we characterize, especially in the area of, say, pulp and paper and cellulosic materials, recognizing the challenges within the province of managing the native tree population, amongst other things. Just a couple of housekeeping notes. So this is the second in our series for the characterization at UBC. We do have a mailing list. It will behave itself fully shortly. Please do sign up with the QR code, even if you're getting this via lots of other means. In order for us to maintain activities, we need to show that people are interested. So it will be a low traffic communication. Please sign up, and we've got a number of fun activities in the future. So just two advertising pieces. We will have a full school on characterization tools and techniques. It will be a 3-day program operating in the winter one semester, October 20th to 22nd. And it looks really fun for the planning that we have so far in that space. The second item is January the 30th, 2026. We will have a half-day, I think it is, symposia and discussion forum for characterization in the clean energy transition. This is a joint activity with the Net Zero Create, led by Professor Chad Sinclair, who is a cluster member, and the cluster itself. So our cluster is to bring together people interested in characterization, and so it's a fantastic pleasure to bring one of our colleagues from effectively experts in X-ray computing tomography and runs a facility over in BPI pulp and paper, chibi mixture of these things. So James Drummond, who has a huge amount of experience managing a facility, imaging cool things, dealing with the complicated questions of researchers. And I think the core focus of the techniques today is going to be linking across optical electron microscopy and X-ray techniques to really tell the full picture of materials. So it's a great pleasure. Please take us away, James.
Thank you very much, Ben. Appreciate that. Appreciate you calling me an expert. I never liked that term, but you have to accept it, because the legal definition of an expert, I found out, is someone who knows more than the average person. So okay, we're experts. We're all experts here. Pleasure to see so many of you, as Ben said, on such a beautiful day, and what would have been a nice, perfect day to take off. Bridge yourself to the long weekend.
Just click, sorry, Zoom is taken. Just click in the middle of it.
What's that?
Just, yeah, great.
Okay.
Sure. Maybe.
There we go. Okay. So this is a ridiculous title, because that's a textbook, that's a course. In fact, there are textbooks, there are courses you can take, but when I think of this challenge, it's like how to begin. I don't know if you've seen it. I saw on YouTube a little short of some again, an expert telling how to begin a talk, and this expert ignored all the advice that we're commonly given to say, my name's James, I'm here to talk about imaging cellulose materials. They said, no, you need to start with the words that have been used for eons to start any story in English, which is once upon a time. So I thought, oh, let's try it today. So once upon a time, in a long ago era called the 1970s, there was this young person, happens to be me. I have time traveled to be here with you. And I was in grade 6. And in grade 6, we got to study a unit on science. In those days, this is what a report card looked like. Your teacher judged you, usually quite harshly. And I draw your attention to the science comment to give you my qualifications to be here. James shows skill in his use of the microscope and in preparation of stained slides for observation. That was nice to find when my mom said, here's all your junk. And I went through my report cards and go, okay, I showed some aptitude at least. However, if you look up at the top in science where it says, right, displays an inquiring mind, well established, that's good. Understands concepts sometimes. And I think that's true today, still always constant learning. Organize and presents data well, not so good. You can be the judge today. As Ben mentioned, I'm in the Pulp and Paper Center, Bioproducts Institute, Chemical Biological Engineering. Mark Martinez is my boss, although he doesn't like me calling him that. We work together. We have some imaging resources there, light microscopy, a couple of optical sectioning techniques, confocal. The PI is Forrest Stover for that. Optical coherence tomography, which is what the ophthalmologist uses to get a cross-sectional image of your retina. It's an interferometry technique. But the kind of the centerpiece is the X-ray tomograph. And I'll talk a lot more about that later. This has all been in the context of kind of an industry university consortium project around reducing energy use in mechanical pulping. And so I've worked with lots of great colleagues, a postdoctoral fellow, Aurelian Savelis, our PhD student, Sam Brown, who you're going to hear speak in the next talk in the series. Recently graduated master's student, Louis Mason, McMaster professor, Andre Filion, Elisa Ferreira, postdoc, Anderson Vega, who is PhD student. I'm going to show some of what he's doing. Professor Emily Cranston, and of course, Mark. So the context I'm going to give you here is mostly in terms of pulp and paper, and you can, shape whatever insights you get to your particular needs. But I've been fortunate enough to play in a really small sandbox for a really long time. And so these are some of the things that I've been able to work on. Pulping and paper making, very simple. Paper making, we're taking an organized lignocellulosic fibrous material. You see a wood disc there. It's a piece of softwood. We can see here what we recognize from temperate zone growth, like we're in a temperate region, climatic region. The trees grow year by year. There's growing seasons and then dormancy. So we get these so-called annual rains. We've all been taught from a young age, oh, you can count and get an estimate of the age of a stem from these rains. And note the color of wood is usually kind of a brown or tan, it could be quite dark brown. And we'll get into that later. But basically, we take this apart. It's got fibrous, elongated cells oriented up the long stem of the tree. And we're trying to break those out of that structure, rearrange them into new structure paper. So here's a scanning electron micrograph of a 3-plane view of just a note paper like you're writing on right now. And we can see that indeed it is a fibrous structure. It's planar, quite a complex structure. Where do we get to lignocellulose? I could call this lignocellulosic imaging, but it's one of those things that all lignocellulosic materials are cellulosic materials, but not all cellulosic materials are lignocellulosic materials. So lignocellulose, what's our source? Mainly here in this context, as Ben mentioned, we have this vast resource of trees. What are they made out of? Chemical composition. Here you see a brief breakdown. Cellulose, which we're interested in today, 40 to 50%. There's these lower molecular weight sugars-based materials called hemicelluloses, around 20 to 30%. Lignin, which is what imparts the brown color to wood, 20 to 30%. And then there's also some materials in the tree which are either taken up as the tree takes solution up from the soil, or the tree produces for its own uses. There's starches, stored foods, there's resins, all kinds of things. And then there can be some inorganic material, some of which comes up into the wood structure just as the tree draws nutrients up, or we end up with organics in our raw materials as it's being harvested and sand and grit gets into the structure. And there's just a nice view of redwoods in Redwood Park in South Surrey. If you've never been there, I recommend it. So what is cellulose, really briefly? Polymer of glucose. We all know about photosynthesis. Trees make sugar in the leaves. It's joined together in a very specific way, which is what gives it its properties. These beta-1,4 linkages create a linear polymer. These long chains of cellulose are aggregated in the cell wall into microfibrils. These have crystalline and amorphous regions. And we think of what those crystalline regions are, dimensions of the crystallites we can get out of them. They're nanomaterials. And I read that cellulose is the most abundant biopolymer on Earth. Lignin you can think of as a reinforcing material. It's like the matrix. It's like the resin in a fiberglass, infiltrates the structure and gives it rigidity. It also links to hemicellulose and then cellulose. You can think of it in broad terms as glue. It's thermoplastic. And this was interesting reading. It is supposed to be the second most abundant biopolymer on Earth, but apparently chitin makes a case. And I have no idea who's making these measurements. I can't keep track of how much milk I have in my fridge, let alone how much lignin there is on Earth. So you're familiar with the challenges of working with this material. If you do, it's organic. It's low contrast in most imaging techniques. It's translucent. Light will go through it to one extent or another. Hygroscopic, fibers will swell or shrink when they're below the so-called fiber saturation point. That's how much moisture can get in between these cellulose fibrils and swell the structure. So you need to have some stability, and that's why paper testing is done under, certain conditions. Paper has to be conditioned to a certain level before you can reliably test it. This is going to affect the properties, obviously. It's not conductive. Ben's seminar was excellent, so you now all know about scanning electron microscopy and all the ways of preparing samples. It's non-conductive, so if you're going to want to image it in an electron beam, you have to mitigate that. So coatings, very common approach, gold, palladium, other coatings as available. Low voltage, low accelerating voltage is possible. So it's something to bear in mind. And it's a robust material, but it is susceptible to beam damage and charging effects in the SEM. I live with a therapist. My spouse is a therapist. So I am reminded all the time, challenges are also opportunities, and we'll see that. So let's talk about fiber structure. There's our softwood wood disc. See the bark on the outside going to the center of the tree. In pulping, either by chemical or mechanical means, we liberate those. So these are the cells. These are the bulk of a softwood, is these long, slender cells. If we were to look at one segment of that cell wall, we would see that it's a layered structure. And this has implications for what we can do in terms of imaging. Going from the outside in, we have the middle lamella, which is mostly lignin. It's kind of a layer, and this is why I say the term glue, between the cells in the wood matrix. And lignin rich. If we go into the fiber wall proper, there's a primary wall where there's kind of loosely arranged cellulose fibrils, not really highly aligned. And there's all kinds of other materials in there, pectins, etc. Most of the cell wall is a so-called secondary wall layer. On the outside of it, there's the S1, and the cellulose fibrils are crisscrossed at a fairly large angle to the long axis of the fiber, and there's two different helical arrangements going there, crisscross, S and Z. If we go into the next layer, this is the thickest wall layer in the wood cell wall, the so-called S2, and because it's the largest, it controls the properties. And that's the fibril angle, if you see there, is quite extreme for illustrative purposes, but usually it's more aligned with the long axis of the fiber. Then there's a thin S3 layer inside with fibrils arranged, cellulose arranged at a fairly large angle with respect to the long axis. And this is a scanning electron micrograph of one pulp fiber where the outer wall layers have been stripped away, and we can see this fibril angle and measure it. And there's all kinds of methods for characterizing fibril angle, and they can be quite involved, but it is an important material property because it gives directional properties to the fiber, the shrinkage, the swelling, as well as the strength properties. These cells are much stronger in tensile along the long axis than they are perpendicular to the long axis. And swelling and shrinkage will go like that. So Anisotropy is what I call it. I think other people like the term orthotropy. Here's the techniques that I've had experience with in evaluating cellulosic materials, light microscopy, SEM, now micro CT. And I'm going to just give you a little bit of a commercial for scanography. And I want to say that in general, in any microscopy, the most important thing is not the instrument, it's the knowledge of the material. So if you've been studying something, before you even look at a microscope, you bring a lot to it. And I know when people bring me materials, metals, I struggle because it's like, I don't necessarily know what I'm looking at. And that's the whole point of it. You're learning by looking. What I like about microscopy is it's this kind of circular thing where you know a certain amount of material, you look at it, you learn more, you keep going back. And then you can take all these techniques, decide which is the appropriate one to give you the information you want. So I would say that don't be intimidated by the microscopes. That's the easy part to learn. Your specific knowledge in your area of study is the most important. So you're an expert. I always say this, a humble plea for light microscopy. It gets forgotten because it's not glamorous anymore. Been around since the 1600s. But there are so many uses for imaging cellulosic and other materials. You have all kinds of ways to manipulate a beam of light. And also you have color information, all kinds of information that you don't get once you go into SEM or micro CT or other techniques, which essentially give you a grayscale image. So we can do transmitted reflected, bright field, dark field, polarized light, plain polarized light, circularly polarized light, phase contrast or differential interference contrast to look at really thin materials or living cells, and a multitude of staining and stains and staining methods. And then there's all kinds of microscopes, depending on what scale you're interested in, stereo microscopes, macroscopes, compound microscopes, and they're usually a lot easier to get access to than higher end instruments. And can also just inform you. It's good to look at things in multiple ways. The more ways you've seen a thing, the more you understand about it. And then it can direct you to the appropriate, more so-called high-level techniques, although trying to understand light is really challenging. This is just, I'll breeze through this because if anybody wants to refer to it later, but wood samples have their own challenges just to get at the stuff because it's tough material. So you have to reduce your sample appropriately with tools which have their own inherent layer of danger. So always take care, get expert advice. I will give you this tip, which most of you probably know. Dry wood splits most easily in the radial plane. We see here this wood block, the bark on the outside, and we see here these lines coming radially from the center to the outside. Those are structures called wood rays. They're horizontally oriented cellular elements that the tree uses to conduct water and materials in and out and store food. So along that plane, it represents kind of a natural zone of weakness. So if you're going to split something, try and split it along those lines. If you want to make a section block to look at it in the SEM, you reduce your sample to small size, and then you want to saturate it with water to make the cutting easier. So that's usually done just by soaking overnight, submerging in water. I wish I had invested in single-edged stainless steel razor blades. I use so many of them in prepping samples that it's not funny, and they can be very useful for even just making hand sections. You don't always have to go to the highest level of technique to get qualitative information. When you want quantitative information or the best information, obviously then you want more high-level preparation techniques. And then solvent exchange and air drying helps to prevent the wood from splitting, cracking too much. If you want to look at pulp fibers, you can also make them in the lab using peracetic acid. Again, read all the STSs, take all the precautions, work in a fume hood, and you can take small matchstick-sized wood samples, liberate the fibers, and you can study them. You get nice delignified fibers. These are aspen pulp fibers, and they're about 1 millimeter in length. So characterization, we can do all kinds of levels of characterization. If you know what to look for, you can identify the wood genus or species by the wood morphology. Here we have a cross-section of hardwood. This is white oak. See your hardwood, softwood structure is very simple. Most of the tree is one type of cell. In hardwoods, cells are specialized. Water conduction is these large vessel elements, kind of act like water mains to draw fiber up and draw water up. Then there's fibers here, which function as structural support. Again, here's these radially oriented, horizontally oriented cells for distribution of water, sap, storing food. And if you're interested, there's plenty of good books on how to identify wood just with a hand lens. And I have this book. And I saw this poster in the lab where I was giving a seminar on identification, and I liked it so much I asked them to give me a copy. So now you're experts in identifying wood. Going into more advanced techniques, sectioning the microtome and looking at the various planes in wood. We study these various planes, cross-section plane, tangential plane, and we can see the morphological features. Here's the cross-section of these wood cells. In softwood, they're called longitudinal tracheids. In pulp and paper, we just generically use the term fiber for everything. And in a sense, it is correct because they are fiber cells. The definition of fiber cells is thin and elongated. So we can see here one annual growth rate, growth starting here in the spring. Large diameter thin walled cells are being produced by the tree as the season progresses and growth slows down. The expansion of these cells diminishes, and we end up with smaller diameter, thicker walled cells. Early wood and late wood are the terms, but it's this, you see this, it's just a density effect. This thicker band, denser band of material is what creates that appearance of a ring to the eye. It's just strictly on a density basis. So it'll look darker brown here than in the early section. We can see here a feature called the resin canal in spruces, larches, pines, and Douglas fir. It's a regular feature, and it's filled with a specific kind of resin that the tree produces, and it helps protect the tree against invasive organisms, fungi, insects, etc. In those species where this is a regular feature, if you look in the tangential section, you will find horizontally oriented resin canals, which produce these really nice spindle-shaped structures called fusiform rays. Again, all of these are diagnostic for species. We've done a lot of raw material characterization, looking at fiber morphology. The morphology dictates what the performance of the fiber will be, or the properties of the fiber will be. Here's two SEM images of sections, and they've been delimited so that we're there on the white oak. We're looking at 2 annual rings, and the same for the birch here. We can digitize that, isolate the vessel elements, and in this case, we were interested in vessel dimensions and arrangement. In wood science, they talk about diffuse porous, so the porosity is kind of the same across the growth ring, and ring porous, where it's basically the largest vessel elements are lined up with the early wood part of the growth ring. And again, we could follow these structures through into pulp, chemical pulp from softwood and hardwood. And you can see here again, because 95% of the tree is just these longitudinal tracheids, these fibers, and they are longer than they are in hardwoods. 3 millimeters is just a rough kind of ballpark way to keep it in your head, versus hardwoods, which have much shorter fibers, around 1 millimeter, can be somewhat longer, somewhat shorter. Like everything in life, it varies. So again, now you can see these vessel elements come out into pulp, and they look like penne pasta. Is what I think of. That shows my bias. I love pasta. We can do characterization of genus by looking at a pulp. We didn't make it ourselves, but if we look at a craft pulp that's got hardwoods in it, we can look at the vessel elements, and their morphology is diagnostic. So in birch, if this is one vessel element in the tree, there would be a chain of these going up. Where they join is called the perforation plate. You can see these fine bars. That's a scalariform perforation plate, and that's a diagnostic indicator, as well as the copious pitting and the small pitting here on that part of the vessel wall. Whereas aspen just has an open end, simple perforation plate, and some characteristic pitting. So we can separate those as birch species or populous species. So, and in Canada, it's going to most mostly be trembling aspen. Similarly, softwood, we can do the same thing by looking at the pitting on the radial side of a pulp fiber. This is where the rays go across, where they're crossing against these long fibers. You get characteristic pits. And by looking at the size and the shape of those, you can differentiate species groups. So Picea spruce, pine, you can even distinguish pine between hard pine and soft pine. Hard pines are pines that have needles in groups of 2 or 3, so-called diploxylon, and soft pine have needles in groups of 5. And they have different types of pits. Those pits are referred to as pinoid pits in hard pine and fenestriform window-like in the soft pine. So simple diagnostics. Again, we talked about different ways to manipulate a beam of light. Polarized light is very useful for looking at pulp fibers. And because of that highly aligned nature, the fiber wall itself will act as a polarizer. And one of the useful things you see there on the right is looking at dislocations, disruptions in that regular structure that are caused by mechanical treatment. This fiber here is a lab-made pulp fiber, nice and straight. You'll see there's some disruptions here. Any tree, when it's growing, will have growth stresses. It will have movement, so there'll be some little slight dislocations. Even though I've been told by my material science friends, don't use the term dislocation because it refers to disruptions in crystal lattice. So bear with me. This has been burned in my head for 30 years. So let's call it disruptions then. So here we see very severe effects. Differences, changes in the alignment of those cellulose fibrils. And so some work has been done to quantify that. So there's opportunities there. Again, scanning electron microscopy, Ben pointed out in his excellent seminar, great surface imaging tool, surface and subsurface. These are freeze-dried fibers we're looking at in the SEM after various treatments. And you already know, you're now already experts in fiber morphology. We've exposed the S2 wall here, and we could see that a very small fibril angle. This is a nice kind of straight fiber, would have pretty good tensile strength, I would imagine. But here we can see mechanical treatments of peeling strips of that S2 wall layer. And it's interesting, as Ben in the seminar said, because these are small, you basically are going to get your electron beams going to go through some of these. So you're not going to see it's like right here, almost transparent, despite having been coated. And then on the right, you can see other fibers where the outer wall layer is still here. There's the underlying secondary wall. But this outer wall layer, because of that crisscross arrangement of fibrils, when you put mechanical energy into it, kind of stretch out. And that's what we see here. It's been loosened from the fiber surface. Yeah, and that's what we call fibrillation is a term you'll hear in pulp and paper all the time. Has implications in interfiber bonding and paper strength. Okay, so we've been looking at surfaces. We want to look inside, and we don't have a micro CT or a fib or other things. We have to physically section it. So how are we going to do that? People often come to me and say, well, I can just cut it with scissors, right? And I always say, please don't, I beg you. Even though the cut might look nice and clean to the eye, you'll find that it's basically fused and smeared. As again, I said, I'm a big proponent of single iterator blades for hand sectioning. With practice, you can actually get quite nice results that give you a quick look at these kinds of materials. But if you want the highest quality, you're going to have to embed the structure with an epoxy resin to give it support while you're sectioning it, however you're going to do that. Years ago, developed a method for embedding and polishing and etching samples for secondary electron imaging. I'll show you that. You want to use a low viscosity epoxy. One I used to use is Spurs resin. Since I've got a micro CT, I haven't embedded anything in 5 years because I don't need to, and it's wonderful. So it is challenging, but sometimes you need to do this. So any low viscosity resin, our friends at bioimaging are experts in this, and they can give you good advice on the latest resins. Of course, there are other options. There's optical sectioning techniques like confocal, or if you have access to the focused ion beam, which we have here on campus, micro CT, AFM, there's all kinds of instruments, synchrotrons. But again, I'm a big believer in starting simple and then getting complicated as needed. Again, looking at the internal structure of fiber and paper, here's embedding and etching method. So here we can use metallurgical molds, just like you use for metal samples, bed large samples of paper, polish them with graded abrasives like you would a metal sample, and then etch away a little bit of the block face with an epoxy solvent, coat it, dry it, coat it, and then you can image this in secondary electron mode. So it gives you a very nice image, and the bulk of the structure is still held by this block of epoxy. And we've done measurements and assessing that, so it really does hold the structure largely intact. It's funny, our PhD student, Sam, was doing his literature review, and he came across a reference to this paper, and they described the method as tedious, to which I can only say, I know, I've done it. So bear that in mind. But it is useful for looking at characterizing materials. You want to, whatever technique you want to minimize artifacts. Can't avoid them entirely, but you want to minimize that. You want to minimize disruption of the structure, moving of things, shrinking or swelling. Can't remember, I can never find the exact reference. I was at a conference and I heard a guy from the Royal Microscopical Society say, all microscopy is an artifact. And I have never forgotten that. And I love that statement. I wish I could properly attribute it. So something always to bear in mind when you're interacting with something in all these ways, you know, there's not going to be zero effect. Here, looking at morphology, again, characterization, these are laboratory-made papers that we use to evaluate strength and optical properties, and then we can also examine them microscopically to correlate what we get of physical test data with the morphology. These are 60 gram per square meter hand sheets, so that's the mass per unit area. It's the same between these two sheets, exact same magnification. And all that's different is the wood species. So Douglas fir, prime lumber species, known for having very thick cell walls, less collapsible, versus Western red cedar, which is very large diameter, thin walled cells. And you can appreciate that if you have a thin pipe with a large diameter, it's much easier to crush that than it is a smaller diameter pipe with a very thick wall. And again, these differences can be quantified. We can take it all the way to embedding pulp fibers and sectioning them, this SEM or light microscope, and looking at the internal effects of refining treatments. There's a laboratory refiner which basically just kind of spins around and massages the fibers, kind of a rolling action. And you look at the internal structure, because we have this cellular cellulose layered structure in the cell wall. You can see here that its delaminations are quite possible. And here we see that this particular treatment does create these delaminations. So another way to characterize it. And again, I'll reference Ben's talk. He talked about secondary electron imaging versus backscatter electron imaging. This is applied to for higher grades of paper. If you see a glossy magazine, it will have fillers in it, will have coating on it to make the surface smooth. You can see here, this is the base sheet of the paper. You can see the topography is actually quite extreme. So in order to get the highest quality printing, you want a very smooth surface, and also for the ink to stay at the surface rather than move into the sheet. So these will be things like calcium carbonate, clay, and these coatings. And again, to look at it in secondary electron mode, but in backscattered electron mode, you get enhanced contrast of the inorganics versus the organic fiber. This is a very old image. And the advances in backscatter detectors and instruments, this is not the greatest backscattered electron image. And you can see it's done at 15 kV. Now you can get really nice backscattered images at very low kV. So if you go and try this, you'll find that you get a very nice result. But then you can then you can segment that quite easily and look at variations in coating thickness. In fact, you don't need to etch if you're looking at inorganics. You can just embed them, polish the section, and do backscatter. And you get much better contrast because the epoxy and the fiber are a lot closer in composition than the coating is. So you get much better contrast. Fiber characterization of internal structures. You can use the light microscope and SEM. There's a little correlative work. On the right is a stained section of aspen from the top side of a leaning stem. Trees have mechanisms to correct. If you've ever seen, you go in the forest, you'll see a tree that's kind of goes this way and then it straightens up. Softwoods and hardwoods both have mechanisms for the tree to produce specific types of cells to correct for that lean. In a hardwood, on the top section of that curve, you would find what is called tension wood. Oh, got that. And basically it produces kind of like an additional layer of highly crystalline cellulose, really high tensile strength material, and almost kind of like it pulls itself upright. I don't have the softwood one here, but it basically builds up material on the underside and kind of pushes itself up straight. With differential staining, we can see that. I deleted a slide because I was running out of time. This is Herzberg stain. So it's an iodine-based stain. It will stain cellulosic tissues this purple color, lignified tissues this gold color. So you can immediately separate and say, okay, what's the dominant thing here? And then we can even look at these fibers in the SEM, and you can see here this layer. It's a so-called gelatinous layer, even though it's actually highly crystalline cellulose. It's kind of like having a cottonwood fiber stuck inside a wood fiber, which ends up creating this material of high tensile strength. We can characterize things like decay and rot. There you see a wood chip in the top corner, and the white areas, we can again section, embed, section, apply basic green stain. Cellulosic tissue is yellow, lignified tissue is green. You can even see here, those little dots are cross sections of fungal hyphae. We can characterize fiber treatments by looking at it either in the light microscope, scanning electron microscope. These are rejects from the primary stage of making mechanical pulp, where the wood is defibered by mechanical action. Looking at this, we can tell how the fibers are separating from the wood matrix. Here's the middle lamella, stained dark, lignin stain, make it look dark. And we see the fibers are separating nicely from the wood matrix. Again, polarized light, because of the alignment of those different alignment of the cell wall layers. This is circularly polarized light. You can make the S3 and the S1 and the S3 layers shine up brightly to get an assessment. And again, you can look at paper structure. This is an example of temperature gradient calendared paper. Paper is passed between high temperature rolls to create that surface smoothness in the absence of coating. You have extreme heat here, which plasticizes this layer, helps it collapse, and that layer, as opposed to the internal structure, which remains bulky. And again, all that stuff can be quantified. Gotta stay on track. If you don't have a flatbed scanner, get one. It makes a great macro camera. This is just a free tip included with the seminar. It's nothing really to do with photos, but makes a great macro camera. Even inconsistent illumination, you try and set up a camera and lights and get a nice evenly illuminated picture of anything, you just for sample documentation. This can do it very readily. The image is inherently calibrated. Scanner will have a pixel per inch rating, so you know what size your pixels are. It's simple and fast and reproducible, and even if you get a really good one, it's inexpensive compared to even just a decent consumer digital camera. I recommend making yourself a little dark box like this so you can get a nice black background for your samples, because many samples, especially if they're translucent, you'll get internal reflection effects. And then you also have a scanner as a bonus, all the other things you can do with it. This is an example just showing differences in two papers from the same print run. And just from product quality, you can see your differences in ink density, ink holdout, show through. You can see print showing through from the other side of the paper versus this one. but then quite severe mottle in the shadow areas. You can also use it for particle dimensions scanner. So we can deposit particles, in this case fibers, and do quantification quite readily. You can get a nice high contrast image, segment, and analyze. Talking more high-end techniques, Ben talked about different types of SEMs and emitters. These would be images from a field emission SEM, Schottky type thermionic emission of cellulose crystallites. So we take those cellulose molecules, hydrolyze them, and they break down into their crystallites. And these are 1 microliter drops deposited on glass, coated, and then imaged in the field emission SEM. You can see the scale bar there, 500 nanometers. We have wood-derived cellulose and tunicate-derived cellulose. Tunicates are marine invertebrates. They are the only animals that can make cellulose. And of course, the morphology of the cellulose they make differs from that of wood. You can image sheets of cellulose nanocrystal films with polarized light. And you get all kinds of information, including measuring the fingerprint pattern, which tells you the chiral pitch of that chiral pneumatic structure as the layer by layer, as you go through the film, it's changing a little bit until it goes through one complete rotation in terms of orientation of those cellulose crystallites. And that's what makes CNC films iridescent, like a butterfly wing. So all kinds of interesting things. In the interest of time, I'm going to skip. I don't want a short shrift X-ray microtomography. Here's our tomograph in the Pulp and Paper Center. The big lead-lined box. If we look inside, we can see that we have an X-ray source and a detector. It's just an electron gun, and it hits a target and generates an X-ray cone, which then goes through the sample into the detector assembly. So we have objectives and a camera, although the objectives are not really directly analogous to a light microscope objective. And then we have a motorized stage, and there's our sample. And the sample is now our lab mascot. It's a Playmobil man that I found in a couch that I was throwing away. It belonged to my son, who's now 32. And it made the perfect sample for understanding 3D data sets for us. Making sure after any kind of maintenance, we put that in, we do a quick scan. Is everything sharp? Also, because we have a sample that has immediately recognizable morphology and is asymmetrical in all axes, when you get a 3D data set and import it into different software, the axes are assigned somewhat arbitrarily, we found. So what you thought was your Z axis, now this software decides that's the Y axis. And if you don't know the material and there's no indication of the material what the axes are, you're lost. So this is a very helpful thing to always come back to this. Okay, where are we? And it makes a cool picture. Everybody likes it. So X-ray microtomography. Source, shine X-rays through. Some are absorbed, one extent or another, or not absorbed, and we get a 2D X-ray image. We're all used to looking at these kind of images. In CT scanning, medical CT scanning, you have a source and detector that spins around a stationary sample, or you have multiple sources and detectors in a ring all around. So you get all these different angles of views, which are then reconstructed. Here, we just simply rotate the sample, very fine increments, get thousands of projections, reconstruct them into this stack of 2D slices, which go from the bottom to the top of the volume as in the Zeiss ecosystem. Of course, you can render it in 3D. Here's the showstopper. This is our Playmobil man animated. Because it's a 3D data set, you can reslice it any way you want. So now we can slice through in this plane, kind of a cross section, transverse section. Now we'll go to a sagittal section and look through this way, come back out. And that was done by our talented student, Sam, who you will hear speak. Takeaway from this slide is we can produce pixel values of 60 to 0.3 microns with our machine. As soon as people hear 0.3 microns, that's 300 nanometers, to go, well, let's scan everything at 300 nanometers. In this particular instrument, when you do that, your scans become exceedingly long. Your field of view is about 250 microns. So very limitation. So it's usually very specialized cases, but we have done that. Typically, we work in the 1 to 2 micron pixel range, which gives you a 1 to 2 millimeter field of view. But we can look at very large objects. You just then are using a larger pixel value. And in any microscopy technique, your samples have to get smaller and smaller to optimize imaging. Some of you have been through that with me. As I said, I haven't embedded wood in a long time, or paper, because now we have a tomograph. We can get cross section quite nicely. And again, this is the same volume on the right. It's just been resliced. So now we're looking at the radial plane, and now you can see those rays, radio-oriented structures, all the pitting. And actually, if you stop that in the right place, you could do identification on that, tell what genus of wood species you're looking at. And of course, usually for just display purposes, because it's cool and people like to see it, you can render it in 3D. Most of our work has been looking at paper sheets. One of the nice things about X-rays is that you could assemble, depending on your field of view and your pixel value and the size of your sample, you can have multiple samples in one field of view. So here, 3 papers, 3 different treatments. And it's aimed at increasing what we call bulk. So we want the sheet to expand. So you have the sheets all imaged under the same conditions at the same time. And then again, you can process these images, binarize, and do quantification. And there's just a nice, again, for display 3D render. The challenge with these data sets is analysis of it. So, and that's, I always hand off a 2 gigabyte file to someone and go have fun. Try and run this on your laptop. We have had all kinds of talented students over the years, and this is a very non-trivial problem, but trying to basically simply label every single fiber in that paper structure. And I've included the references here. I'm going to end on this. One of the interesting things we've done here, which is kind of weird, is X-ray scans are conventionally done in air. So you just have your samples. It makes it very easy to prepare your samples as long as it's not going to move and it's mounted securely. You can do X-ray on it. We have been trying to look at where the fine material in a sheet goes. So we've been trying to enhance contrast because we have this low contrast, trying to enhance it by labeling with iron. So Anderson has been working on that. And so here we have like about 25% labeled fines, very thin material dispersed in a sheet. And this is just a conventional scan in air. And you can see there's some indication that that's brighter than that, but there's already so little variation between the fiber and our air background that we decided, well, let's do something analogous to refractive index matching in light microscopy, where you can make certain structures, if you match the refractive index, you can render them invisible. Here it's hard to do because you have to match density and composition, but we found an immersion oil, which is a hydrocarbon oil. It's non-polar, so it won't swell the fibers. And so we put this in a syringe, scanned in air, fill the syringe with oil, let it soak in, scan it again. And you can see here, just by the addition of oil, now you do have enhanced contrast here. And that is enough to give a foothold for integer segmentation to be used. We've also have Lewis, one of our students, has been doing machine learning segmentation on it, but even then it offers significant advantages over air. And here's an example when we have tagged fibers in a sheet scanned in oil. That's the contrast, and then segmentation, separation is pretty easy. So thanks for listening. I think I made it. Now you all have an honorary degree in wood science, if you don't have a wood science degree already. Again, as Ben pointed out, there's a wide range of experience and technology available at UBC, which is why efforts like this are so valuable. That's the thing I've noticed most about. I came from industry-funded R&D. The level of collaboration that I've experienced here in the 5 years has been so wonderful. A real sense of team, not just lip service. It's a real team approach here, which I love. So we've got bioimaging, got the materials, electron microscopy lab, Center for High Throughput Phenogenomics, and more. So, and yeah, don't forget the light microscope and get a flatbed scanner. So yeah, with that, I'll thank you for your attention, and make sure you'll want to come and see Sam. He's really good. Thank you.
Thank you very much, James. Slightly just in terms of Sam's talk, I think it's on August the 28th. I think in that we have one talk in between in the series, but that's not to dampen. I think Sam's talk looks wonderful. Thank you very much. A small comment. It's always beautiful seeing someone who really cares about the art form of microscopy and the presentation and framing. And I hope people in the audience really get that if you take these pictures and make them look as easy to